Assalamu alaikum, dear students. I welcome you to the second lecture of probability and stochastic processes. My name is Dr. Muhammad Akmal Bhatt. In this lecture, we will continue with our discussion of what probability is and how we deal with problems related to probability theory. In the previous lecture, we discussed that we live in an unpredictable world where outcomes of events cannot be predicted precisely in advance because there are so many factors that affect the outcomes of the events under study. And we have either zero knowledge or partial knowledge about these factors. And because of this lack of knowledge, we cannot precisely predict what the outcome is going to be. So we deal with these kind of situations with our experience of previous happenings of similar events. So because of our knowledge of what happened in similar previous situations, we try to fit a model to the problem under study, and we apply mathematical tools to come up with meaningful assertions about the long-term average behavior of unpredictable events. In this lecture, we'll continue with the mathematical tools that we need to study probability theory. In the last lecture, we started our discussion of set theory, and let's continue with that. The next topic that we are going to talk about today is Venn diagram. Venn diagram is a graphical tool to represent sets and their mutual relationship. The kind of mutual relationships that we are interested in are whether there are any common elements between two sets, or if elements of one set, all of them are contained in the other set, which is called the subset. If elements of one set, all of them are present in another set, then this first set is a subset of the other set. And similar other relationships are graphically represented very nicely in Venn diagrams. So in Venn diagram, a set is represented by simply connected closed curve. What I mean by simply connected is that the boundary of the curve does not intersect with itself. To know more about simply connected and not simply connected curves, please study your handouts that you will get with this course. So in Venn diagram, the set is represented by a simply connected closed curve, and the interior of that curve represents all the elements in the set. Please note that the size of the closed curve does not have anything to do with cardinality of the set. A set with very few elements can be represented with a bigger closed curve, and a possibly infinite set can be represented by a smaller closed curve. So in Venn diagram, when you have more than one sets, you draw them in such a way that the mutual relationship, that is, if there are common elements, that is, if the intersection is non-empty, such relationships are properly represented in the graphical diagram. As you see in the first slide, if we have a set A which contains elements 1, 2 and 3, we can represent this graphically in Venn diagram as a closed figure, an ellipse with elements 1, 2 and 3 written inside the ellipse. It's not necessary to write these elements inside the ellipse because it is understood that the interior of this ellipse represents all the elements in the set. Another thing that you will see is that we usually put these closed figures inside a large rectangle and write U in the rectangle. This rectangle represents a so-called universal set, and importance of this universal set will be clear if we see that all these sets which are graphically represented must have a superset, the universal set, because certain operations are defined with the relationship that this U has with the given set. For example, if we have a set A and we want to find out the complement of this set A. As you know, the complement of set contains all elements which are not in the given set. As you see in the next slide, if the given set has elements 1, 2, 3, 4 and 5, then the set A complement, which represents all the elements not in the set, can have number 7 because it's not in the given set. It can have letters A, B, C because certainly these letters are not in the given set, but it can have many more other possibly irrelevant things. For example, it can have a few animals in Lahore Zoo. It has nothing to do with the study of this set which contained 1, 2, 3, 4, 5, but certainly the complement of this set can have animals in Lahore Zoo or animals roaming in the streets of the city. But that's not the context of the problem. So the U, bigger triangle, the universal set, is a superset, and the complement of a given set contains all elements which are in U but not in the given set A. So in our reference, if we have our U for this particular problem to be a set of numbers between 1 and 10, natural numbers between 1 and 10, 1, 2, 3, 4, 5 up to 10, then the complement of the given set A will be only numbers 6, 7, 8, 9 and 10. So we need this bigger rectangular U and call it a universal set, and it relates to all the sets under study in a sense that this universal set is a superset of all sets under study, and then complement of any set is only those elements which are not in the given set but in the universal set. There are other relationships between sets that can be nicely represented in graphical way using Venn diagrams. Suppose we have two sets and they have certain elements common between them, then we draw these two closed figures representing these two sets with some overlapping area, and that overlapping area represents the intersection of the two sets. And the total area between two curves, the overlapping area and the area between two sets which is not overlapping, the whole thing represents the union of the set. As you know, there are other operations like difference of two sets that can also be represented in Venn diagrams. For more details, you should see any mathematics book on set theory or the study material, the study notes that you receive with this course. After the Venn diagram, let's move on to the next topic, which is power set. Power set is a special set related to a given set in this way that power set contains sets. It contains all possible subsets of a given set. As you will see in the slide, if we have a set A which contains element 1 and 2, then its power set contains 4 subsets of A. They are empty set, the set with element 1, the set with element 2, and the set with element 1 and 2, the set A itself. So the power set of a set, a small set like A, which contains only 2 elements, contains 4 elements, including empty set and the set itself. On the same slide, as you see, if we have A to be a set with 3 elements, 1, 2 and 3, then its power set will contain 2 raised to power 3, 8 elements, and each element will be a possible subset of given set A. And if you represent each element as a binary bit in a 3-bit number, as you see in slide B2, B1, B0, this is 3-bit number, and if any of these bits is 1, then the corresponding subset will have that element. For example, if all bits are 0, B2, B1, B0 is 0, we are talking about binary number 0, then this represents an empty set because none of the three elements will be present in the set. And if we are looking at a binary number 111, which is 7, which implies that bits B2, B1 and B0 are all 1, then all elements of set A, 1, 2, 3 will be in the subset which has a correspondence between itself and the number 7, which is the set itself. So the point is that a set A which has m elements will have a power set which will contain 2 raised to power m elements, and these elements will be possible subsets of the given set A. That is good if the set under consideration is a finite set. What if the set is infinite set? For example, the set of natural numbers, the set of real numbers, etc. Then the possible collection of all the subsets of these infinite set is definitely infinite, possibly bigger than the given set. And this leads to a very interesting observation, as you will see in the next slide. Suppose the set A is a finite set and its cardinality, that is the total number of elements in A is P, where P is a finite number. Then Q is the cardinality of power set of A, and this is 2 raised to power P, and if P is finite, then obviously Q is also finite. But if we move to set of natural numbers, if A is R, which is set of natural numbers 1, 2, 3, 4, 5 up to infinity, then what about cardinality of the power set of natural numbers? To see this, let's represent each subset, each possible subset of set of natural numbers in a special way as a decimal number, a number smaller than 1. It is 0 point, then elements of this number. As you will see on the slide, that this number is 0 point B1, B2, B3, B4, B5, B6, so on and so forth up to infinity. What these B1, B2, B3 represent is whether the corresponding element in the natural set is present in the subset or not. For example, if we are writing a number 0 point B1 and B1 is equal to 1, then natural number 1 is present in that subset. Similarly, if there is a number 0 point B1, B2 and B2 is 0, then the second element in natural number 2 is not present in the set. So if we have an infinite sequence of these digits B1, B2, B3, B4, so on and so forth, and each one represents whether corresponding natural number is present in the subset or not, then total possible number of subsets is equal to total possible sequence of these digits B1, B2, B3. And if they are considered to be digits of a binary decimal fractional number between 0 and 1, then any number between 0 and 1 can be represented as an infinite sequence of these binary digits B1, B2, where B1, B2 can either be 0 or 1. So I hope you can see that this collection of 0 point B1, B2, B3 sequences is uncountably infinite because it represents every possible number between 0 and 1. It represents the interval between 0 and 1, with 0 is included in the interval and 1 is not. So this interval on the real line is represented by this sequence of digits. So cardinality of power set of natural numbers is equivalent to cardinality of interval 0, 1, which is equal to cardinality of the set of all real numbers R. So 2 raised to power the cardinality of natural number is cardinality of real number. That's very interesting, and if you want to go deeper into these ideas of cardinalities and power sets, you should look up a good textbook on number theory. The next thing that we are going to talk about is Cartesian product. This is also related to set theory. The Cartesian product is formed when we use two or more sets, and the result is also a set. And the elements of this resulting set are ordered collection of elements coming from the sets that are used to form the Cartesian product. For example, if we have two small sets A and B, with elements of A being three alphabets X, Y, and Z, and elements of B being three numbers 1, 2, and 3. Then the Cartesian product will be a set, and its elements will be ordered pairs. In each ordered pair, first element will come from the first set A, so it will be an alphabet, and the second element will come from the second set B, so it will be a number. So all the elements which will be in the Cartesian product will be x1, x2, x3, y1, y2, y3, and z1, z2, and z3. It's quite easy to see that the Cartesian product can be thought of as a rectangular array, with rows being represented with elements of the first set and columns being represented with elements of the second set. Then in this rectangular array, the element at ith row and jth column is an ordered pair, where the first element is ith element of the first set and the second element is jth element of the second set. So the total size of this array will be the size of the first set multiplied by the size of the second set. What we are talking about is cardinality of the Cartesian product. If we know the cardinality of the two sets which are being used to form the Cartesian product, then what is the cardinality? What is the size of the Cartesian product that we form from these two sets? If the two sets being used in the Cartesian product are finite, if the cardinality of first set is P, which is a finite number, and cardinality of the second set is Q, which is also a finite number, then the cardinality of the Cartesian product will be P multiplied by Q, and this will also be finite. And if the two sets being used have same cardinality, which is a finite number, say P, then the cardinality of the Cartesian product is P square. This cardinality is important in the context of probability theory because we will use it to find the total size of the Cartesian product that we form by using two sets. What happens if the sets being used in the Cartesian product are infinite? Then what about the cardinality of the resulting set? Suppose the two sets that we are going to use are sets of integers. So we are forming a Cartesian product between sets of integers and sets of integers. The result will be a huge collection of ordered pairs of integers, with first element coming from first set, which is set of integers z, and second element also coming from set of integers z. So this huge collection of ordered pairs of integers will cover an infinite extent rectangular array. What about its cardinality? We know that the cardinality of integers is infinite, but it is a countable infinite. So what will be the cardinality of the Cartesian product of one set of integers with second set of integers? Will it be infinity square? Once again, it is meaningless to talk about infinity square. You should look at your course handout to see the detailed discussion about this, but for now I can tell you that the cardinality of the Cartesian product formed between two sets of integers is same as the cardinality of set of integers. The Cartesian product between z and z is usually denoted by z square, and this superscript 2 over z square has nothing to do with the cardinality of the Cartesian product. It just emphasizes that we are dealing with pairs, and the pairs are formed by two numbers, and both of these numbers are integers. So what about its cardinality? As I said, you should look at the class handouts for detailed discussion, but the Cartesian product formed by using two sets of integers z and z is same, the cardinality of the Cartesian product is same as the cardinality of the sets being used. So cardinality of z square is same as cardinality of z, which implies that if we have an infinite extent array, an infinite, countably infinite set, we can rearrange its element and form an infinite extent two-dimensional array. We can certainly use real numbers to form the Cartesian product. So suppose we use set of real numbers R and set of real numbers R to form the Cartesian product, which gives us a huge collection of pairs of real numbers. First number is a real number and second number is a real number. So this collection of ordered pairs where first and second both numbers are real numbers is usually denoted by R square. And once again, this square, the superscript 2, has nothing to do with cardinality of the Cartesian product. It just says that we are dealing with two real numbers, ordered pair of two real numbers. We can certainly use more than two sets to form Cartesian product. For example, if we use three sets, then the result is a set which is Cartesian product of three sets, and this set has ordered triplets. The elements of this Cartesian product have three entries. First entry coming from the first set, second entry coming from the second set, and the last entry coming from the third set. This is an ordered collection. You cannot swap the position of the entries. Or if you want to involve more than two sets, you can replace one set that is usually used in Cartesian product with a Cartesian product. For example, you can form a Cartesian product between 2D plane and line. Then the first element is an ordered pair, which is coming from the 2D plane, and the second element is a real number. So there are three entries, first two being grouped as pair and then the third entry as real number. But the overall number of elements in this ordered triplet are again 3. Another way to form a Cartesian product between three sets is to form a Cartesian product between a set and 2D plane, the set being the real number. So then this Cartesian product has ordered triplet with first entry being a real number and second entry being a pair of real numbers representing a point in 2D plane. All these three set Cartesian products are equivalent in a sense that they cover the whole 3D space that we live in, with x-axis representing the first number, y-axis representing the second number, and the z-axis representing the third number. So all three Cartesian products are into R, which is simple ordered triplet of three real numbers, or ordered pair of 2D point and a real number, or ordered pair of real number and 2D point. They cover the whole 3D space, but they have their own special characteristics, as we will see when we cover the topic of relations and functions. We have been talking about sets, and sets are formed when we put together similar objects. There is another collection of objects that we were just talking about, which is ordered collection, ordered pair, ordered triplets. This class of objects is called vectors. A vector is formed when we put together in a specific order more than one objects which have some relationship to each other. So a vector is an ordered collection of objects. The Cartesian product is nice because it involves both things, sets and vectors. Suppose you have two small sets A and B. A has elements x and y, two alphabets, and B has two numbers, 1 and 2. Then their Cartesian product is a set, and in this set there are 4 elements, and the 4 elements are formed as ordered pairs with first entry coming from alphabet x or y and the second entry coming from number 1 and 2. So if you are putting together this Cartesian product, you have 4 entries, you can swap the position of these 4 ordered pairs, but in each ordered pair the 2 entries must come in a specific order, like alphabet first, number second. So x comma 1 is in this Cartesian product, but 1 comma x is not. So vectors and sets are two types of collection of objects that we deal with in mathematical analysis of probability theory. These sets and vectors have real life applications also. And let me give you a nice example where the difference between sets and vectors will be clear. Suppose somebody asks you to list all of your real uncles, that is, brothers of your father and brothers of your sister. And suppose you have 5 real uncles, 3 from your mother's side, 2 from your father's side. And if you want to put together this set, you are free to put either maternal uncles first or paternal uncles first, or you can even mix all these 5 names and the set will still be set of your uncles because it represents similar items and there is no predefined sequence of entries that you should observe. Now, if somebody asks you to list your lineage, your ancestry, that is your father, his father, that's your grandfather, his father, which is your great-grandfather, and so on and so forth. If you start listing these people, then you better list them in a specific order, like first your father, then grandfather, then great-grandfather, so on and so forth, all the way till Adam. And if you switch around these entries, then this collection with random entries will not make sense as a lineage. You can call this random collection as a set of your ancestors, but people will not be interested in this random collection. They would like to know who is coming first in time and who is coming later. By the way, how far can you go up your lineage? Most people know the name of their grandfather. Some people will know name of their great-grandfather or great-great-great-grandfather, but it's rare for people to have their ancestors' name at level 6 and beyond. There is one exception though. If you claim to be a Sayyid, then you might have a valuable document placed somewhere with other family valuables which lists all the people in your ancestry going all the way to 6th century AD. One more thing, these lineage, these documents which list your lineage usually just list male ancestors. It's extremely rare to have documented the female ancestors. So all those ladies who nurtured and nursed your ancestors are forgotten. Well, that's the world we live in. The Cartesian product between two sets lists all possible pairs that can be formed by taking first element from the first set and second element from the second set. This is too huge a collection, and sometimes we are interested in a certain subset of this Cartesian product which meets a certain criterion. So a subset of a Cartesian product is called a relation. It relates the elements from the first set and the elements from a second set in a certain way, in such a way that all these elements they follow a certain rule. So a subset of Cartesian product is a relation. Any subset is a relation, and by default the Cartesian product itself is also a relation. There are two important sets that we talk about when we talk about relations. The first set is called domain of a relation. The domain of a relation is a subset of first set. That is, if we are forming a Cartesian product between set A and set B and then take a subset of this Cartesian product, then all the elements in this subset which are being used from the first set form the set domain, and definitely this set is subset of set A. Similarly, all the elements in the relationship which are coming from the second set are called range. So in a relation, elements of domain are paired with elements of range. So if you look at all the pairs in a relation, then the first element comes from domain and the second element comes from range, and domain is subset of first set, range is subset of second set. Please note that it is not necessary for every element in domain to form a pair with every element in range. It's possible that some of the pairs of elements of domain and range are missing. It is acceptable and the relationship is still a valid relationship. In the next slide, you will see a few relations that are formed over R2, the set of real numbers. As you know, that the Cartesian product R2 is formed when we take pairs, ordered pairs, with first number coming from the first set and the second number coming from the second set. So if both sets are set of real numbers R, then the Cartesian product is R2, the whole 2D plane. And a relation in this 2D plane is any subset of 2D plane. In the slide, you will see a few relations on R2. The first relation R1 is set of all those points which are bounded between x greater than minus 5 and x less than 5, and then x and y must also satisfy the next constraint, that is, their sum should be larger than 0 and smaller than 1. If you try to figure this out, you will see that this represents top right hand corner of a square in the 2D plane. The second relation R2 defines a solid filled circle centered at origin with a radius of 25. And the third relation, well, I'm not going to tell you, you should work this out and sketch this on a 2D plane to see what subset of 2D plane this third relation represents. As I said that a relation in R2 is any subset of 2D plane, so in this slide you will see three graphical representations of three relations. First is a collection of lines, second is a collection of filled rectangles, and third is a filled ellipse. Once again, a relation is a subset of Cartesian product, and in case of Cartesian product being R2, any subset of 2D plane is a valid relation. These Cartesian products and relations also play their role in everyday life. We humans are related to other humans through a single bond of humanity. Every human is related to the other human. But there are certain relations which are more well defined than this generic bond of humanity. So let's look at the next slide, which shows few relations that can be formed between humans who are alive. So let's take set A, set of all adult living human males, and let's take set B as set of all adult living human females. Then the Cartesian product that we are interested in is ordered pair, where the first element is any living human male and second element is any living human female. This is a huge collection. This ordered pair, this Cartesian product, this collection of ordered pair is so huge, it's enormous. But let's look at a few interesting subsets of this Cartesian product. The first subset, the first relation is R1, which is all those pairs of living adult human males and females such that the male is of the same religion as the female. So for a given female, the relation contains all the females which are of the same religion as the male. This relation also contains quite a large collection of pairs. For one particular male, it may have millions of females which share the same religious faith. Let's look at the second relation, which is slightly more restrictive. It is all those pairs of male and female such that they live in the same city. So if you take any male A, then all the collection of pairs of that male and other females who live in the city could be in a million range or slightly less or more. The third relationship is even more restrictive. It says that R3, the third relationship, contains all males and females such that the male has met the female at least once. So for a certain male A, it contains all the females that he has met during his lifetime. Let's look at the next relation, which is relation 4. Relation 4 is interesting. It says it contains all pairs of males and females such that male wants to marry B. He is interested in B. For a certain male A, this subset of Cartesian product, this relation contains maybe a dozen or so females. Well, if the male is optimistic, it can contain 100 of females, but one has to be realistic. So the fifth relation, R5, is that it contains all those pairs of males and females where A, the male, has a realistic chance of getting married to B. So this is quite a small set compared to the previous one. And lastly, the sixth relation, R6, is a pair of male and female where they are actually married. So this is very small set. For each male, there is possibly one, and if you are living in this society, possibly more than 1, 2, 3, or in rare cases, 4 females which are married to a given male. So all these relations between males and females are subset of a huge Cartesian product which is formed by taking first element as a living adult human male and second element as adult living human female. The last thing that we are going to talk about in this lecture is functions, which is related to Cartesian products and relations. As I told you, a relation is a subset of Cartesian product, any subset. But a function is a special type of relation with very strict restriction that for all the pairs in a function, every domain element being used should have associated with it a unique element of range. So if I give you that this element of the domain is in this relation, then you can immediately find out what will be the range element associated with it. So knowing the domain element gives you all the information needed to find the associated range element. Because domain elements get mapped to range element, the functions are also called mappings. Because if you know the domain element, you use this mapping to get the range element that is associated with this domain element. Functions are also represented by equations. If the mapping follows a certain mathematical rule, then this mathematical rule can be written down as an equation, and this equation defines the relationship between domain element and the range element. In this slide, for example, you will see a function f1 which is a special subset of R2, the 2D plane, and it has all pairs of real numbers xy such that x is between 0 and 10. And if you know x, you can find y by using this equation, y is equal to 3x plus 2. So this equation gives you value of y once you put in the value of x. Functions are subsets of Cartesian products. Functions are also called mappings. Functions can be described by equations, and functions can also be described by graphs. What is a graph? It is a graphical representation of a subset of R2. So if on R2 you draw a subset graphically, then this graph may represent a function. Suppose there is a point x1, y1 on the graph. Then we know that x1 belongs to domain and y1 belongs to range. And this pair x1, y1 is in the relation, that restricted relation we are considering as a function. As I told you, the function is a special restricted relation in which if you know the value of domain element, you can get to the uniquely defined value of the range element. If a graph meets this requirement, it represents graph of a function. Otherwise, it does not. To test it, what we do use is popularly called vertical line test. So if you have a graph of a function, you draw a vertical line intersecting it. And if this vertical line intersects the graph only at one point, then that point defines the relationship between domain and range element. And if this vertical line cuts the graph at more than one point, then for one domain point you have multiple range points, which is not allowed for a function. It is allowed for a relation, but not for a function. As I said, the functions can be represented by equations and graphs. And in the next slide, you will see graphs of three functions. The first is a straight line, second and third are curves. But the important thing about these three graphs is that if you draw a vertical line anywhere on the x-axis, it will cut the graph at only one point. You can certainly define functions with domains other than the set of real numbers and range also other than set of real numbers. For example, you can define a function over 2D plane where the domain elements are pair of two real numbers x and y, and the range is just a real number. So the domain is 2D plane and range is just a real number. So this type of function is called a surface because it is defined over plane and gives a variable height for each point in domain. So it defines a kind of surface over 2D plane. There is another variation to subsets of R3, which are functions where the domain comes from real line and range is pair of two numbers, ordered pair of two numbers or an element in 2D space. Actually, this is a pair of two functions where you start with element of domain and you use first function to get the first number, and the second function to get the second number, and you put these numbers in an ordered manner, and you take this ordered pair of numbers and call it an element in range. So range is now two-dimensional. An example of this type of function is complex exponential, where the domain is any real number and the real part is cosine of that number, and the imaginary part, which is the second element in the ordered pair, is the sine of that number. We will come and talk about this complex exponential when we will be studying characteristic functions. Functions also play an important part in everyday life. If we see two things are related to each other, we should see if there is a unique relationship, if we can define the second element in a unique manner given the information about the first element. Let's take the example of relationship between males and females. So if the domain is males and the range is females, then look at this relation. Pair of all males and females where male is son of the female. So A comma B are all the pairs of males and females, and in this relation all those pairs are used where A is son of B. This is a function. Knowing the son, you can uniquely determine who his mother is. Look, if we have more than one son in the domain and they have a common mother, that is okay. A mother can have multiple sons in the domain, but for each element in the domain, for each son, the mother is uniquely defined. So this is a function, even though multiple elements of domain get mapped to a single element in the range. Let's look another relation between males and females, where A, the male, is married to female B. Is this a function? Unfortunately not. If we were talking about some Western progressive society which strictly follows rules of monogamy, then this is a function. Knowing male, you can uniquely determine his wife. But in our society, unfortunately, males get away with marrying more than one woman. Maybe in 2,000-3,000 years things will change, but so far things like that do happen. So in our society, knowing a male does not give you a unique mapping to a female who is his wife. But if you look at another Cartesian product where females are the domain and males are range, then a pair B comma A, where B is the first element, a female, A is the second element, a male, and B is married to A, then this is a function. Knowing a female in our society or in any other uniquely tells you who her husband is. A female cannot have more than one husband. So female comma male, if they are married, this forms a function. But male comma female, if they are married, in some societies they form a function, in others it's just a relation. So functions are special restrictive subsets of Cartesian product with a unique rule that knowing the domain element gives you all the information needed to find the range element. To rephrase all the things we covered in this lecture, we started with Cartesian product, which is a set formed by taking two or more sets and using elements from these sets and making ordered collections and putting those as elements of Cartesian product. So a Cartesian product has in an ordered manner listed all elements of all the sets which can be combined to make an ordered couple, triplet, or higher dimensional vectors. Then we talked about vectors and sets. Then we talked about relations, which are subsets of Cartesian products. And then we talked about functions, which are very restrictive class of relations. All these things will be used in mathematical analysis of probability theory. We would like to know what are the quantities, how they are related. If we need to find a special restrictive subset of all the possible relations, we'll do that, and then we'll define functions which relate in a unique way elements of the first set with the elements of the second set. And with the help of these mathematical tools, we will try to solve the problems of probability theory and stochastic processes. Thank you.